It's great to have Shannon back here on campus. He came from the University of Oregon as a undergraduate and in graduate school on National Science Foundation Fellowship. And when he was an undergraduate, he also had a Berry and Goldwater Scholar Fellowship there as well. He worked here for several years. He'll straighten that out. It's actually more like 4 or 5 years, I think. But then after that, went to Caltech and was there worked with Barry Atwater and also with Martin A. Lewis. Was doing work on photovoltaic, artificial photosynthesis, and other related projects to that. He's had a strong interest in energy storage for a long time, making nanostructure with high precision types of systems, and particularly looking at interfaces and how electrons get transferred from one part of the system to another part. He is while he was at Caltech, he got the Kavli Nanoscience Institute Prize for a postdoctoral, which is an open postdoctoral competition among the postdocs who are at Caltech. And then beyond that, he got an offer to go back to Oregon, to the University of Oregon, where he's currently assistant professor in chemistry, which may change, is changing at the present time. He's one of the 18 DuPont Young Professors worldwide, and in 2014 was a Contrail Scholar. So today he's going to talk about energy storage, electrochemical energy storage, design principles for oxide electrocatalysts, and aqueous supercapacitors. Welcome back.
Thank you, Galen. So it's awesome to be back in Santa Barbara. It's a great place to visit, and I got to talk to most of my thesis committee today, which is always fun to catch up and learn what's going on. So today I'm going to talk about the things that have really got me excited in our research group over the last couple years. And if you have questions, feel free to interrupt me or save them to the end. I don't care either way. So at the big picture, in the big picture, we're motivated by energy. I won't go into this in much detail, but many people I'm sure have seen this graph, but it's nice to show in any case. This is the US, of course, and this is the area you'd cover with a photovoltaic or photoelectrochemical or some sort of solar conversion device if you wanted to get all the power we use in the US. So it's a big area. And there's good reason to be thinking about solar because that's where the energy is. The other sources of renewables probably won't get us to what we need to be at to do everything for the world. So I like to just motivate this really quickly. So we work on both conversion and storage concepts for solar and related energy technologies. But if you look at the solar photovoltaic market, it's kind of remarkable what's happened in the last few years. So the cost of solar photovoltaics has sort of plummeted in the last factor of 2 or 3 lower. So right now, you can install photovoltaics in Southern California in the Mojave Desert, and the levelized cost of that energy is about 11 cents per kilowatt hour, which is pretty similar to what it costs to generate it with a new gas-fired power plant or something like that. It's really remarkable, and it's in the next decade or something we're going to hit cost parity. But the challenge is actually storing that energy costs 2 or 3 times that per the levelized cost to build the storage capacity, the battery bank, the pumped water. It's expensive, so that's why the solar photovoltaic manufacturers actually see that as a market cap for them. They can't get over sort of 15, 20% of electricity in this country without massive storage. They know that. I was just at a conference, Sunshot conference for the DOE, and basically the CTO of First Solar, the biggest solar company in the US, said, look, photovoltaic tech, we're going to get to this. We're going to hit cost parity. You guys have to figure out a way to store it without costing 3 times as much as it costs to make the electricity at the outset. So there's a lot of need here, and there's accordingly a lot of research. So we work on both things. This is just an overview slide. I apologize, it's a little busy. I'm not going to talk about a few of the things. We have a pretty active program, actually. Really, I got interested in these high-performance semiconductors when I was here and learning all the great stuff that happens here. And we've been working on basically how to grow 3-5 semiconductors using non-metal organic chemical vapor deposition techniques, so low-cost 3-5 semiconductor growth, and have a concept tandem cell we're working on of 3,5 on silicon with a so-called vapor transport process. It's really quite interesting, going very well. We have a big center in Oregon, an NSF center. It's a phase 2 CCI, focused all on solution processed large area films that have applications as conducting oxides and various coatings for solar and other technologies, smart windows. And today I'm going to talk about the electrochemical aspects of our group, very much focused on energy storage. One of them I'm going to spend a lot of time talking about the electrocatalysis of oxygen. And the other one is this work that is going on actually in collaboration with Galen's group here in Santa Barbara, looking at some new concepts in electrochemical capacitors. Okay, so the first thing I wanted to mention or to cover was this, this idea of a solar to fuel device. And this, if you could build something like this sort of schematic, the idea is that you take some sort of photovoltaic element, some sort of semiconductor junction that's absorbing light, and the holes go to one side and make oxygen, and the electrons go to the other side and make hydrogen. So if you could integrate this thing, it might eventually look like a sheet of black plastic with little chunks of semiconductor in it, with these catalysts on either side bubbling off hydrogen and oxygen when you shine sunlight on it. The idea is that you integrate storage with conversion. And today I'm going to focus down and talk about one aspect, and that's this electrochemical water oxidation reaction, which we've been studying in some detail. And it's very important in these systems because this step is traditionally slow. But it's important in a much broader context as well. So oxygen electrocatalysis actually limits the efficiency of many different energy storage types of devices. So I mentioned this water splitting cell. In a fuel cell, you need to do oxygen reduction. So you need to take O2 and make it into water in a fuel cell. And so the kinetics of that is one of the major efficiency losses, the slow kinetics. So understanding oxygen electrochemistry is important there. It's important for air-breathing batteries. So lithium-air batteries and related systems. You're doing oxygen electrochemistry. And also in direct application of the things I'm going to talk about, this is a picture from a company called Proton On-Site. And they have developed some of the most cost-competitive large-scale electrolysis systems for directly generating hydrogen and oxygen from water using electricity. And so in their systems, they've developed a market where they sell the hydrogen, for example, to the semiconductor industry that needs high-purity hydrogen delivered on demand. They don't want to store the hydrogen because it's dangerous, and they can make it directly in very high purity using electrochemistry because there's no sulfur and things that you might find in reformed hydrogen. And so this is actually a demo unit they put together. This is a fueling station, so you can go up here and drive up to their plant in Connecticut, which I've been there, and you can fuel your hydrogen car there with electrolysis-derived hydrogen. And it's really interesting there. The cost modeling is showing that they're probably going to get below $10 a kilogram just with current electricity prices for hydrogen, which is pretty respectable. It's a kilogram of hydrogen is about a gallon of gasoline in energy content. So there's still a ways to go. So if we can improve this technology, it's important for that as well. Okay, so when I started a few years ago, I knew there was a lot of opportunity to understand and develop these catalysts, but there's also a ton of work. So if you look back, people have been studying oxygen electrocatalysis for 50 or 60 years. And there's tons of work out there. But if you look at it and you try to figure out what the most active catalysts are and why, you can come to many different conclusions depending on which papers you read. And the challenge is that these are very complicated systems. So when you're doing oxygen electrochemistry, you're evolving oxygen from water, the catalysts people usually study are these very high surface area materials. And the reason is because if you have a high surface area, you have a lot of active sites per geometric area, and you can pass significant currents at fairly low current densities. But the challenge is understanding materials like this. They have these high surface areas, make it difficult to identify what are actually the active sites. You have to move things through the high surface area material. You have to move the electrons, you have to move the mass that you generate, the oxygen you generate, so they're difficult to study. And so this is a challenging problem. It's been worked on for a long time. And people still don't understand the role of composition, as I'll show you. conductivity, the solid state structure, the porosity on how these oxygen catalysts work. So it's complicated. So one thing that I learned from Galen, actually, that really helped on this project is when you have a really hard problem, you just hire really good people and you ask them to solve it. And it works great. So my first student to join my group was Lena. She's graduated now and at Berkeley doing a postdoc. And so I basically, we wanted to figure out what were some simple ways we could try to make well-defined catalysts, how do we could determine what are the basic parameters that determines which ones are more active than others, and how do we eventually design better ones. And so to start, I'm going to show you some extremely simple data that turned out to be really useful for us and led us on a very interesting study. Okay, so what Lena did is very simple. We said, well, if we want to understand oxygen electrocatalysis, and we think there's these factors of electron transport through high surface area materials, of mass transport, let's just make very thin films of the various monometallic transition metal oxides. We'll do experiments on an electrochemical quartz crystal microbalance, so we can just weigh the amount of material we put down, so we know it's an oscillator, and the resonance frequency tells you the mass of the material there, and you can measure it to sub-monolayer precision, so you can see if it's dissolving or if something else is plating. You can see if it's changing with time. If it's a very thin film, the lateral conductivity is not that important because it's thin. The electrons don't move very far. We're going to use solution processing, just simple salts, surfactant to make relatively smooth, thin films to break the surface tension. The surface area we know because it's basically the real surface area. And gas and ion transport is fast because you don't have a lot of porosity. Okay, so is our approach. And so when we started looking at systems to study, we first looked at what is known about the oxygen evolution reaction. And so this is what's called a volcano plot. This comes from the work of Sergio Trussati. He's an Italian electrochemist, did a lot of beautiful work in this area. And the idea here is that you plot on the y-axis the activity of the catalyst. This is the overpotential relative to thermodynamic potential for evolving oxygen in the electrochemical cell. And so if you have an overpotential at passing a given current density, a given rate of the chemical reaction, you want as small overpotential as possible. That's high activity. You plot this versus some chemical parameter. This is the enthalpy of going from a lower oxidation state oxide to a higher oxidation state oxide. So you're making more metal oxygen bonds. And so the idea is that this enthalpy is related to the metal oxygen bond strength. So this is a classic catalysis principle, that if the rate determining step involves a metal oxygen bond, then there should be some trend in activity with the metal oxygen bond strength. And so here, this is the mechanism. So this is what one of several mechanisms, the one that Jens Norskov uses. He's a big theorist in this area at Stanford now. And so the idea is, okay, if you have water, it's a 4-electron process. So I need to pull 4 electrons off of 2 water molecules, make 4 protons, and then couple the oxygens together, make O2. And it has to happen through 1-electron steps, because nature doesn't transfer many electrons at once. It always does it through 1-electron steps. And so you can do 1 proton, 1 electron, make a hydroxide, bounded to a metal at the surface of the catalyst species here. You can make an oxo, you can react with water, pull off another proton, make a peroxo, eventually make oxygen. And if the metal oxygen bond strength is too strong, the idea is you probably get stuck in one of these intermediates over here. There's a big activation barrier in one of the terminal steps. If the metal oxygen bond strength is too weak, then you never form these initial intermediates to start with. Okay? And so this kind of explains this data. We thought, okay, well, it's interesting. But the materials here are not particularly well defined, and so we're interested in re-examining some of these things. And so one of the things that people had reported is that if you mix cobalt and nickel oxides together, the performance is better. And you could wave your hands and say, well, nickel oxide is on this side of the volcano and cobalt oxide is on this side, so if you mix them together, maybe you have some sort of the right binding strength, and so it's faster because of that reason. Okay, well, there's also a lot of other things that could be going on, so we thought, well, that's a good place to look. So we just started looking carefully, and the first measurements were surprising to us. So we found that we made these thin nanocrystalline films. They're only a few nanometers thick, 2 or 3 nanometers effective thickness, so there's some roughness, and They're a little bit nanocrystalline, but they're thin films on gold electrodes on this quartz crystal microbalances. And we found that cobalt oxide had the worst performance, nickel oxide had the best performance, and there was a linear trend as we added nickel to cobalt. And how you read this graph, this is called the Tafel plot. Again, this is the overpotential to drive the reaction at a given current density. This is on a log scale. So this is the rate of the reaction increasing here, and the driving force, the real electrochemical driving force, the thermodynamic driving force on the y-axis. So good catalysts have points down here and bad up here. Okay, so nickel oxide was the best, cobalt oxide was the worst. There was no synergy. And the other thing that was interesting is the plain nickel oxide electrode we made had much higher activity than we had thought we would see. In fact, if you compare it to the nickel cobalt data from the literature, this nickel cobalt oxide film that was presumably optimized here, and you could get data from many papers and you'd find this very thin film of nickel oxide by itself had performance that was essentially equivalent to this 20 micron thick film of this nickel cobalt oxide. So something was odd here, because the loading's about 1,000-fold less, but the performance was the same. Trying to understand what's going on, certainly wasn't explained by anything we read in these nickel cobalt oxide papers. And so Lena measured the electrochemistry as a function of time. And one thing that we found that was very interesting is that as you ran the voltammetry, the voltammetry changed. This is a cyclic voltammogram, so current density, again, versus overpotential or potential versus a reference electrode. And so what you see is to start with, a very small hump here. This is at the position of oxidation of nickel 2 plus to nickel 3 plus, until you get out to higher potentials and you see an exponential increase in the current, and this is making oxygen. This is the onset of oxygen evolution reaction in these materials. And as you run these nickel oxide thin films, this peak gets larger and larger and larger, and the onset shifts to lower overpotential, so it's becoming a better catalyst. And so this is consistent. This is consistent with I don't know what happened here. Never seen this. Oh, it's really small. That's funny. Sorry about that. This is consistent with the conversion of the nickel oxide electrode, this crystal nickel oxide, into this oxyhydroxide hydroxide phase. So this peak is consistent with the oxidation of all the nickels to nickel 2 plus, from nickel 2 plus to nickel 3 plus. And the fact that peak's growing in is telling us that we're making more of this layered structure. And I'll talk about this more in a second. And so if you go look at the XPS, you find the XPS spectra are exactly as predicted for these layered structures. So you're starting out in these oxide phases, you're making these hydroxide phases. If you do the experiment where you look at the voltammetry after conditioning for some time, after allowing the sample to convert to the extent it does to the oxyhydroxide phases, you find that as you add cobalt, for the pure cobalt sample, for example, the film does not show any of this prefeature because there's no nickel. And as you add more nickel, this feature gets larger. But if you actually measure the number of electrons that go into that oxidation wave and you compare to the total number of ions, nickel ions that are in the film, because we can weigh it. We have it on this quartz crystal microbalance lecture. We can weigh it. We can compare those two. And what we find is that for the pure nickel oxide film, essentially every nickel atom is becoming electrochemically active. But if you add cobalt to the film, it's suppressing that phase transformation. So the nickels are actually getting protected within the cobalt matrix, cobalt spinel matrix. So what we think's going on here is that if you have this pure nickel oxide phase, it actually wants to become an oxyhydroxide, a hydroxide phase. This is sprucite structure. It's a layered structure, and this phase transformation happens. If you have a lot of cobalt, you start making this spinel phase. You can see this in the diffraction, and it doesn't transform in situ to this type of structure. Okay, so that's very simple. So we think this is the structure that's important for catalysis. And this structure is very different from this in that in these crystalline materials, the reaction has to happen at the surface. It has to happen where there's metal ions touching electrolyte. These materials, in a sense, are all surface because ions and electrolyte can permeate, can move between the sheets of these layered double hydroxides. And that's why you can actually measure electrochemically oxidation on every single nickel. Okay, so in principle, you have catalysis throughout the bulk of the film now as you've converted from this crystalline structure, this bulk crystalline structure to this layered, sort of intrinsically electrochemically porous structure. Okay, so now we understood this. We started digging deeper. What's known about the electrochemistry of nickel hydroxide? What's known about electrocatalytic properties? And we actually uncovered some papers that are not as widely appreciated as they should be by Dennis Corrigan. And Dennis was studying nickel hydroxide electrochemistry for batteries. So if anybody has a Prius has a nickel metal hydride battery, and one of the electrodes is actually nickel hydroxide. And GM put a huge amount of effort into developing these nickel hydroxide batteries. And what Dennis found, which was remarkable when we started reading his papers, is, and I got to talk to him actually a few months ago, which was awesome. So he was basically trying to make a reproducible nickel hydroxide electrode, but every time he'd make a nickel hydroxide electrode, he'd charge it, and it would discharge by itself. It would self-discharge at a different rate. So he had a very hard time making a reproducible electrode. And what he found is that the charged nickel hydroxide was making oxygen, so it was driving oxygen evolution reaction, which is what you don't want in a battery. Of course, it's a self-discharge pathway. And what he traced this to is he actually traced this to iron, impurities, in his electrolyte. And so iron had a significant effect on the electrocatalytic activity. Didn't fully understand what it was doing, but it was affecting the rate of self-discharge in these batteries. So we went and looked in our films, and sure enough, they all had iron in them. So not only were we converting from a crystalline material to a layered material, it was reacting with the electrodes, pulling iron impurities out of the electrolyte that are getting incorporated into the structure and changing its activity. Okay, so this is going to be really important in a second. So we did this type of careful study for a lot of different metal oxides. And the surprising thing to us was that these nickel iron materials, so any material that started out with nickel and either accumulated iron via reaction with the electrolyte, impurities, or we put iron in from the beginning, had activities. Now these are on a turnover frequency basis, so it's a sort of intrinsic measurement of activity based on the total number of metal ions at a given driving force that are significantly higher, order of a magnitude higher than the precious metal things that were at the top of that pyramid. So these, in basic media, these nickel iron materials really, we've looked all through the literature. These are the fastest OER, oxygen evolution catalysts out there, these nickel iron oxyhydroxides. They're much higher than iridium oxide and much better than pure cobalt oxide. And so we wanted to understand this. So this is where it starts to get really interesting. So we kind of start out with simple experiments just to give us a framework to understand what the basic reactivity were of these first order transition metals. And then now we have something really interesting to study. Okay, so we published this paper, and it's a simple thing, but it has like a zillion citations now because people all over the world are starting to study in much detail these nickel iron systems now. Again, they were known before, so I wish we had invented them, but we didn't. So we had some various hypotheses about how these systems should work, might work. And so the first one I really like is this, these are layered structures. And if you look at the theory literature, the hypothesis is that to speed up the overall electrochemical reaction, you want to stabilize the peroxide intermediate, so this OOH intermediate. And I thought, these are layered structures, and those intermediates can maybe sit in between the sheets. And that sheet spacing might be about right, so you could have some three-dimensional interaction. Maybe it's like an enzyme or some enzyme pocket or something. So we wanted to, how can we test this? How can we understand whether or not these three-dimensional interactions are important? The other important thing is, of course, if you can change the binding energies with iron doping, alloying, with percent, 10, 20%, you should change the activity. Here's a paper from Alex Bell at Berkeley now. This is where my first student is now working. So she went and worked for our competitor, which is good. And what's interesting is this wave, this nickel 2,3 oxidation wave, its position on the potential axis depends on the amount of iron you alloy in the nickel iron oxyhydroxide. So what that's telling you is you're changing the electronic structure. You're changing the energy at which you can pull electrons out. So you're moving the density of states, the D band or something of the oxyhydroxide. We also wanted to look at the thin film, the actual electronic conductivity, because as I mentioned before, you really do need to be able to move electrons through these films to get them to the active sites. And if this electrical conductivity was sufficiently high, even in thin films, it could make a difference. OK, so the first thing we had to figure out was how to actually get rid of the iron that was coming in unintentionally from the electrolyte. And so when I saw this data, it really blew me away. So we took a glassy carbon rotating disc electrode, really clean, freshly polished, Teflon cell, no glass parts anywhere. Glass has iron in it. It's etched by KOH. You get rid of all your glass. We used the highest purity metal salts and the best KOH, analytical grade KOH you can buy. And you put a nickel hydroxide film on an electrode, and you cycle it. And it's a rotating disc electrode, so you're stirring. And what you find is every cycle, the activity increases. And if you go and look in XPS, you can see iron if you use a magnesium source. And if you just deposit the film, you see no iron. If you put iron in intentionally, you see 2 large peaks. If you cycle it 5 times, this film, you see 5% iron at the surface. So it's amazing. 5% iron just by cycling this thing 5 times in this electrolyte. So it's sucking up every iron that hits the surface. It's going into this structure. Huge affinity for iron. If you do the same experiment but don't apply a potential, you get 2% iron after 10 minutes just sitting in the solution. OK, so this is a problem. So how do we get rid of this? Well, what Lena figured out, came with a nice idea, is that if the nickel hydroxide with no potential applied sucks up iron with high affinity from the electrolyte, let's use that to purify the electrolyte. So what she does is she precipitates nickel hydroxide and shakes her electrolyte in a test tube, centrifuges, decants, use that electrolyte to test the catalyst in thin film. So uses a catalyst in powder form to purify electrolyte that then is used to test the catalyst in thin film form. And now you can cycle forever and you never get any iron in. So now you have a really good control sample. So this was really important. OK, so we wanted to test a few things. So one of the things we wanted to test was the role of structure. So this is from the battery literature. As you precipitate, you form nickel hydroxide, you get this alpha phase. You have disorder between the sheets in the three-dimensional structure. And if you let it sit in the electrolyte for a while in KOH or heat it a little bit, it goes to this beta phase, which is basically more ordered, and it's the structure I've been showing you. There's a number of papers, 4 or 5 papers, that show that the beta phase is more active for OER catalysis than the alpha phase. It's shown here. When you age it, you form the beta phase, it turns on sooner, the peak also shifts to the right. And so this was one of the lines of evidence that I used to argue there must be some interaction, because these sheets are getting ordered and closer together, so it's affecting the activity. Maybe there's a three-dimensional interaction here. But what's interesting is this is similar to what you might expect if iron is incorporated into these structures during this aging process. So we looked at this carefully. So Lena did this aging experiment, crystallizing this nickel hydroxide or nickel iron hydroxide. And if you do the experiment as in the literature, you see the same thing. You crystallize it, you form more crystalline material, the peak shifts over to the right, and the OER activity increases. If you add iron, a lot of iron, and you crystallize it, this is 25% iron, you don't see much change in the voltammetry. Actually, this nickel oxidation wave has shifted over to where it's essentially under the onset of oxygen evolution current. And there's no significant change in the activity with crystallization. If you get every iron ion out of the electrolyte using the method I showed you, What's interesting is it turns into a really, really bad catalyst. So here, the onset of OER activity now is shifted over to almost 500 millivolts overpotential. If you have iron, it's turning on at a little bit over 200 millivolts overpotential. It's 10,000 times worse catalyst without the iron. And furthermore, as you crystallize it, the activity actually decreases. So you start forming the beta phase, you see a new peak grow in that's associated with the beta phase electrochemistry, but the activity decreases. So, actually proved our hypothesis wrong. All these other data were contaminated by irons. This is important for us. So it's also important is that there's probably hundreds of papers on various forms of nickel oxide OER catalysis claiming them to be really good OER catalysts, but it's not the nickel doing the work. The iron's in there somehow contributing. And so we need to understand this better. Here's the diffraction data, basically just showing that as deposited, they're relatively disordered. They crystallize. You get these broad peaks that show you which phases form. And so if you have no iron around, you form this beta nickel hydroxide. If you add iron, you form this layered double hydroxide phases where the layers are actually pushed apart. And the reason they're pushed apart is that the iron substitutes for nickel. And iron's 3 plus in its resting state, nickel's 2 plus. To compensate the charge, you have to have some interlayer anions, and that pushes the sheets apart. And this sheet spacing is sufficiently large that there's really no way this kind of interaction can be happening. So this really shows that my hypothesis was wrong, which, it's good if your students prove you wrong also, as long as they prove you one way or the other. Okay, so what's going on here? So we looked at the electronic conductivity. And so this is a very simple but neat experiment. We take an interdigitated electrode, and it's a bipotentiostat experiment. So what we do is we have an interdigitated electrode array with these gold fingers. We deposit a catalyst film on top of it. This is dried out. That's why it's breaking up into pieces. And then what we do is we apply a small DC voltage offset between the two electrodes. So current is flowing from one electrode to the other. And at the same time, we sweep both their potentials simultaneously relative to a reference electrode up and down. And when we do that, we can measure the conductivity, the intrinsic conductivity of the material, as a function of the charge state of the catalyst. And what you see is that the conductivity is very low when they're in their reduced form, where they're hydroxides. As soon as you oxidize them to oxyhydroxides, you see them become highly conductive. We're not sure if they're degenerate semiconductors or metals. We're doing some of these studies now. And what you find is that the addition of iron actually increases the conductivity 30-fold over the case where iron is rigorously removed. So this is important if you want to understand how to design systems that utilize this catalyst. But it turns out that the conductivity of both phases are both sufficiently high that it cannot explain the differences in activity we see. So there's a big difference in conductivity upon iron incorporation, probably some sort of doping effect, but it does not explain the difference in measured OER activity. Okay, so we're doing other experiments. We're looking at other mixed systems to try to understand the various activity trends we see. So here's some data for an iron cobalt system. And you see very similar trends. So as you incorporate iron into cobalt oxyhydroxide, you see the oxidation wave of the cobalt now shift to higher potentials. You see the activity increase. The change in activity going from ultra-pure cobalt to iron-doped cobalt is not nearly as large as in the nickel systems, but it is significant. We can measure the turnover frequency. Michaela is doing this work, and one thing I love about Michaela is she does lots of experiments, and she does lots of experiments that I don't tell her to do, and every so often there's one that's really, really important. And she did this control experiment looking at the iron oxyhydroxide end member of this series, this solid solution series, or this, we don't know if it's a solid solution, but this, this series of oxyhydroxides, and she did the conductivity measurement. And so this is again the conductivity turning on for the iron cobalt hydroxides. The nickel hydroxides look similar. It's on a log scale now, so it looks a little different. But as soon as you oxidize the cobalt or nickel, the conductivity turns on, it becomes conductive, and then OER can happen out here once it's conductive. And its conductivity is really important because you've got to deliver the electrons or remove the electrons. But if you look at iron by itself, rust, it's a really bad conductor. Not surprising. But what's interesting is that it does become moderately conductive if you polarize it very anodically. You're probably starting to form some iron 4+, and there's maybe some sort of hopping mechanism. So if you push it hard enough, you pull enough electron density out of it, you apply a sufficiently anodic potential, it starts being a little bit conductive. And what's interesting is this onset of conductivity matches well to the onset of OER activity in the bare iron phase. So why that's interesting is it looks like that iron oxyhydroxide is not nearly as bad of a catalyst as people thought. It's a bad electronic conductor. And the electronic conductivity is essentially gating what you measure as the OER activity. Okay, that's important. So how do we think about this now? So we have lots of data that shows that nickel hydroxide is an extremely bad OER catalyst. This is really important if you're doing DFT calculations that are predicting the activity of nickel hydroxide as good. It's not. Iron oxyhydroxide is actually much better, and the low conductivity is really the reason for its low apparent activity. It's very likely that in this type of structure you have basically iron. There's lots of evidence that iron substituting on the nickel sites, they're basically the same ionic radius. It's very likely that you have an iron active site, and that the nickel or cobalt layers are essentially serving as an intrinsically conductive. They've oxidized to oxide, they're conductive sheets. Intrinsically high surface area support. So they're intrinsically high surface area, they're conductive, and you can have these isolated iron sites where the activity is probably taking place. Now, of course, we know there's strong electronic coupling between the iron and nickel because of the changes in the redox peak. That's probably important too. There's recent work unpublished now, but will be soon, I think, from Jens Norskov looking at the change, using density functional theory to look at the change in the binding energies of the iron when it's in the nickel hydroxide lattice. And so, this is a very different way to look at catalysis than thinking about it happening on a surface. And it shows just how important the impurities are. And so I want to drive this home. So if you looked in the literature and you believe something like this, iron oxide, the surface it's hydroxide, oxyhydroxide, it's measured to be a horrible catalyst. Well, if you make a thick film of it and it's an insulator, you can't get any current through it. So of course you're not going to measure any catalysis. So does it really do to this? I don't know. It's not in our book. If you look at work coming out of Argonne, actually it's an extremely good electrochemistry group. They actually assigned a periodic trend to the activity of OER in these hydroxide, oxyhydroxide phases just a couple years ago when we were starting this work. And then, they come to the conclusion that nickel was the best, cobalt was the next best, iron, and then manganese. And they say this is all due to the oxophilicity of the cation, the metal-oxygen bond strength, essentially. That all seems fine, except, if you really do it carefully, the trend is exactly opposite. So if you get all the iron out, the real trend is exactly opposite that's here. This is completely wrong. So it's really interesting to me that basically, by being careful, you can see that we don't understand this reaction yet. And there's a lot more that needs to be done. So nickel is by far the worst. Cobalt's a bit better. Iron is better than both of them. And these phases, which disperse the iron in conductive supports, are the best. And so we have a lot more to do. And this is just the beginning. But I think we've uncovered some things that are really interesting. And I've taken a little longer than I hoped. But so we're working now with some electrolysis companies to try to understand how to integrate these into actual electrolyzers. And we really would like to design better catalysts now that we understand things a little bit better, and we're working on that. Some other things we're doing that I'm not going to talk about is thinking about the interface of these types of catalysts with semiconductor photoelectrodes. And so one neat thing about these catalysts is because all of the ions are electrochemically accessible, you can oxidize or reduce all the metals. They essentially have work functions that float around, that can move around depending on the state of charge, just like a battery material. And so we worked out the theory of how these things interface with semiconductor absorbers. And one of my postdocs actually developed a really cool dual electrode photoelectrochemical method to sort of study these interfaces. And I just wanted to put these up there because we published them in nice journals, and so it's good when you're an assistant professor to brag a little bit. But I'm not going to talk about it any more than that. You guys are supposed to laugh a little bit. You're supposed to be tired. Okay, so the next part I wanted to talk in the last 10 minutes about the work in collaboration with Galen and his group, especially Brian played a big role, and some folks, David G. at Oregon State University. All the work I'm going to talk about, most of the work has really been done by a postdoc that I'm going to mention is by a postdoc in my group, Sangun, who's been really instrumental here. Okay, so the idea is that we want to make a electrochemical double-layer capacitor that has an enhanced capacity due to some Faradaic, some redox process that we want to control. So if you look at a traditional electrochemical double-layer capacitor, it's basically two high surface area porous carbon electrodes separated by a separator. They're on aluminum foil electrodes. And when you polarize them, you make a double layer at the carbon electrolyte interface. It's usually a non-aqueous electrolyte. And that double layer there's an electric field there, which stores energy. And these are commercial. Maxwell's a company, I think, down in San Diego, make a variety of products. And they're used in applications spanning like regenerative braking, emergency doors on airplanes, cold start, load leveling. And the reason people are interested in them is because you can charge and discharge them very fast. So this is called a Ragone plot, applying specific power versus specific energy. And capacitors have very high power, but somewhat low energy. The high power is because all the reactions are happening in electrolyte. There's no solid state intercalation, deintercalation reactions, so you can cycle them very fast and they last a long time. The challenge is that they're actually pretty expensive because the carbons need to be high purity and high porosity. You're using typically flammable organic electrolytes, and they don't store much energy. So what you'd really want to do is get something in this area here. So if you could increase the capacity, marginally actually by a factor of 5 or 10 from an electrochemical capacitor, but maintain a reasonably high rate, you'd have a large application space that is interest. And so our approach is to use soluble redox couples. So here is shown two activated carbon electrodes. On one side, at the negative electrode, you can reduce some species in solution after charging the capacitor. So you charge the capacitor, and you reduce that species. On the other side, you charge the capacitor positively, and then you have the capacitive energy storage, but you're also oxidizing something in solution. You use a redox-active electrolyte instead of an inert electrolyte, and you get extra capacity is the basic idea. The challenge is that now, at this side, you have a large concentration of O prime. On this side, a large concentration of R prime. You have a concentration gradient. That concentration gradient will drive diffusion across the two electrodes. They'll discharge the battery internally. So if you can prevent this self-discharge, you can actually potentially make this work. You also need high power, which means you need to understand diffusion and kinetics of these redox processes in the capacitor architecture. Okay, so in designing these things, we think about what are the design principles. And so we want to target aqueous electrolytes instead of non-aqueous electrolytes because these are inherently safer and potentially much less expensive. We really need to have redox processes that are customized for both negative and positive electrodes because you want the formal potentials where this reaction occurs to be close to the decomposition potentials of your electrolyte to maximize the amount of energy you can store. I'll show you a graph in a second. You want high solubility, so you can have a lot of this stuff within the porous architecture, fast kinetics, stable, and we need to think about how to design for slow self-discharge, and this is non-trivial. I did want to point out that this idea was first actually proposed by FeOOH, and with some related systems, though I'll show you here our implementation is quite different. So here are a number of redox couples we considered. In the white here, this is the area where water is stable. If you have an electrode in this area, you won't make, in this potential region, you won't make oxygen or hydrogen. If you go outside this potential region, you start running the risk of evolving oxygen or hydrogen. And so what you want is you want a redox couple on the cathodic side that's sort of near or right beyond the sort of stability window of the electrolyte. So you can store a significant voltage when you drive a redox reaction. And one series of couples that had not been studied for this purpose are these viologens. And so this is a viologen structure. Methyl viologen is a prototypical example. It's used as a herbicide. You can buy it in 50-pound sacks. It's super cheap. So if you could use something like this, the cost would not be an issue. on the positive electrode side, we got interested in halogens, and I'll show you some data for bromine and iodide that are sort of span the stability window here on the oxidative side. Okay, so we designed a special cell to do these measurements, and what's nice about this cell is it's made completely of inert components. This is a glassy carbon current collector with a shroud of plastic. It's contacted to this activated carbon electrode. And here's the separator between it, that separates it from the other activated carbon electrode. And so you can do your normal 2-electrode device measurements, while at the same time we've incorporated a third reference electrode so that we can measure what the potentials of each electrode are doing relative to some absolute reference potential. I'll show you data in a second. So here's some data for a control electrode. If you just take the carbon and you use an inert electrolyte, potassium sulfate, high purity, you see that as you charge it, this is charging it at a constant current, the cell potential increases linearly with the charge. And that's, of course, C equals Q over V. It's just acting as a capacitor. You can discharge it. You can measure the self-discharge rate. So this is something we're going to compare between the different systems we're looking at. And here, in terms of the remaining energy, you can you can charge it, let it sit for some amount of time, and then self-discharge it, or then discharge it. Sorry, you let it self-discharge for some time, then you discharge it, and you measure how much energy is remaining. And what you can see for these control electrodes, you can get about 50% of the energy remaining after 6 hours of being charged, after being charged. So this is sort of a typical self-discharge rate in a capacitor. It's not nearly as good as a battery. Okay, so what happens when we put electrolytes in? So if you put iodide in, you see something like this. So now the plot is somewhat different. So here, this dashed line is a total cell voltage. That's the voltage between the two current collector rods that are directly connected to the activated carbon electrodes. But we're also simultaneously measuring the potential of the positive electrode and the negative electrode. And the positive electrode, potential does not change much with time. And the reason is because you have this high concentration of Ki, potassium iodide, so you have 1 molar potassium iodide electrolyte, and the formal potential for driving the oxidation of iodide to triiodide is right here. So whenever you put positive charge on that carbon electrode, that positive charge can go into driving this redox reaction. On the negative electrode, however, you see that its potential changes linearly with time, and that's because the potassium ions that migrate to the negative electrode build up in a double layer, and you can't transfer charge to them. So it's a purely capacitive mechanism. If you do the same experiment with bromine, you see similar results, except now bromine has a much more positive formal potential. So you see both a capacitive charging regime and a rollover where you start doing the Faradaic charging of the bromine. That makes perfect sense based on classical electrochemistry. Okay, so that's interesting. So what happens to the self-discharge? And this is where it became quite interesting. So we noticed, and I showed you the halogen data for a reason, is that if you put Ki in, 1 molar Ki or 1 molar Kbr, the self-discharge rates after 6 hours were not, in some cases, much better, and with bromine only slightly worse than the control cell with no redox couple at all. So for some reason, you weren't getting this internal shuttling effect happening with these electrolytes. And so we wanted to understand this a little bit better, so we did a couple control experiments. So we used some well-known outer sphere, spherical 1-electron redox couples. And we wanted to look at whether, for example, the charge of the redox species made a difference. So if you think about this electrode, if this is the positive electrode, there's a bunch of positive charge sitting on the carbon. It's been electrostatically charged positive, and to counteract that positive charge, you need negative charge in the double layer. And that double layer charge could come from the iodide or bromide counterions. Now, if you put in a redox species that's also positively charged, electrostatically, it would not want to stay in this nanoporous host that's positively charged also. And so what you see is if you do that, you see that the cell discharges in a few minutes. So if you use a positively charged couple, this cobalt trisbipyridine, it discharges in a few minutes. But if you use an iron complex that's also negatively charged, while it doesn't self-discharge as fast as the positively charged couple, it still self-discharges a lot faster than these couples. And so what we think is going on, and we need to test this in more detail, is we think that the slow self-discharge rate is really due to a specific absorption. So this is activated carbon. These are big polarizable anions, especially the tribromide, triiodide, the oxidation products. There's probably a fairly strong driving force for absorbing these on the activated carbon, and that's preventing the oxidized product from diffusing across the electrode. And so we're doing some experiments to confirm this, but it seems very, very likely. Okay, so we also were studying electrolytes for the other electrode, and I just have 2 more minutes. And so we got similar data for these methyl-viologen couples. So again, you can see that the voltammetry starts to roll over as you charge it at the formal potential for driving methyl-viologen reduction. The self-discharge rate is also fairly slow, and that's not the case for other outer sphere electron couple redox couples we studied. And we think, again, the methyl-viologen structure is fairly planar, especially once you reduce it. It becomes a singly positively charged, becomes planar, conjugated. It probably has a pretty strong physical absorption onto the planar graphite that makes up the activated carbon. So we think that's, again, playing a role. We can now, that we've sort of studied these different processes, we've studied different electrolytes, you can combine both of them together. And you see data as expected. You see both at the positive electrode and the negative electrode evidence for capacitive charging in this linear regime, Faradaic charging in this sort of flat regime at the formal potentials. You can do a voltammetry experiment. It's very similar, where you sweep the potential of the 2 electrodes and you measure the individual potentials relative to a reference, and you see again the capacitive regime. But once this total cell potential gets sufficiently large, you start driving the Faradaic, reversible Faradaic chemistry. And these potentials are separated about 1.4 volts, which is about ideal and aqueous electrolyte. You look at the self-discharge data, and the methyl-viologen bromide system, while its self-discharge is a little bit worse than the control capacitor, it's still pretty good at short times, and not worse at all than a commercial aqueous capacitor that we got from a Celergy. It's not nearly as good as the organic cells from Maxwell. But what's interesting is if you replace the methyl-viologen with heptyl-viologen, this was known from electrochromic literature to have better cyclability. It also has lower solubility, so once you make the singly reduced species, it's going to absorb probably stronger on the activated carbon. Now, the self-discharge rate is actually very slow. The problem with this is, of course, its concentration isn't that high. So we can compare this now on this Rigoni plot that I showed you right at the beginning. This is the same data with our data overlapped, and we actually designed a second type of cell to do this. So where one of the challenges in the capacitor literature is nobody ever accounts for the volume and weight of their electrolyte in their measurements. They always just measure the carbon mass. But it's really important here because it's an active component. So we had to make a cell that you could really quantitatively get at the electrolyte mass. So when you do this, you can see that the methyl-viologen bromide system I showed you here is really starting to access this area where we wanted to access. And we think, with further optimization, further understanding, we can drive the capacity and the power up higher. One challenge is the viologen system decays with time. It's actually known that the reduced form of the viologen can dimerize and become inactive. And the heptyl-viologen system I showed you before is extremely stable over thousands of cycles. The challenge is, of course, increasing the concentration. And Brian's actually, I'm not going to, I guess I'll skip this, but Brian did some beautiful modeling to show that we can really increase the capacity a lot if we can increase the solubility and keep the self-discharge process from dominating, keep the specific absorption going on. Okay, so I think, gone a little bit over, so I want to stop there and take any questions. Thank you so much for listening to me. It's great to be back here.
Questions? Yeah.
For the iron, nickel, and cobalt oxide, have there been many other studies where I'd assume you get iron impurities in other types of oxides?
Uh-huh.
Has anybody ever
So we've started to try to look at for other systems. I think the cobalt and nickel systems are particularly a big effect because they seem to readily incorporate. The metal hydroxide bonds aren't that strong, so the exchange rates with the iron in solution seem to be pretty fast, and the ion sizes are similar, and they just go in very fast. So I'm not sure. It's hard to deconvolute everything people have measured. So we've tried to look at some manganese systems. We think that might be another good candidate because manganese oxide is also conductive, can be made pretty porous, probably alloy it with iron, so we're doing that right now. There's not a ton of other systems out there. You start actually going through the periodic table pretty fast when you're looking for base stability, conductivity. But yeah, if you have suggestions, be curious.
Did you measure the bulk resistivity of the carbon electrode and the contact resistance with the current collector?
Yeah, so we have that data. I don't have it off the top of my head, but we definitely have the impedance data and the bulk electroresistivity data at the current densities we're operating at. Those don't appear to be huge components to the.
So that at low current density, that is not a factor.
In these Rigoni plots, I suspect it is up here. We're driving them pretty fast. But I can't give you a really good answer as to what fraction of the loss in power we try to drive at those rates is due to that voltage loss of that specific resistance. That's one of the things we still need to have a good measurement of. But yeah, that's a good question.
Can I ask another one?
Yeah.
Did you consider using carbon nanotube electrode structure?
Yeah. One of the challenges.
Do you have any data on that?
Not yet, but Brian, if you ask Brian in a little bit, he might have some data for you because we thought about carbon nanotubes, also graphene. One of the reasons is exactly getting at this conductivity issue. So how we've done the measurement, the conductivity isn't that important because we have back contact to the whole pellet of activated carbon. In an actual device, of course, if you put it on aluminum foil, that's fine, but these aluminum foil is not going to be stable in water. It'll oxidize. So we need a different current collector. And so that's actually a challenge in aqueous systems. How do you get a lightweight current collector? You can use stainless steel. Some people use silver paste. But if you start thinking about manufacturing, actually a carbon nanotube, weaved carbon nanotube, or a graphene type current collector might be really compelling because it could be really stable under these conditions and also conductive and lightweight. So.
From what I remember, I was under the impression that the oxygen evolution reaction in alkaline electrolytes was dictated, electrocatalysis was dictated by the breakage of that substrate hydroxide bond, followed by absorption of hydrogen peroxide. Do you have any evidence that the incorporation of iron into these nickel hydroxides modulates that bond strength?
So there's evidence from the calculations, from the density functional theory calculations. So what they show is that, and I don't know how much to believe it because it can't always predict the trends that are measured. So, but what they show is that you take iron, so they measure several things. Well, first of all, they don't use the rate determining step you just said.
Okay.
There's a big there's lots of different mechanisms that people have drawn, and people interpret the Tafel data, but the Tafel slopes are basically continuous. They're not, you see Tafel slopes of all things. So I'm actually, my jury's still out on me whether that is really telling us what the rate determining step is. But I think, that could be for sure. And then to follow up on the bond strength question, what the theory shows is that if you put iron into nickel and you compare the metal peroxide bond strength of iron in the nickel hydroxide lattice versus iron by itself, it increases the bond strength, which is what you would predict in their Norskov framework model to increase the activity. So basically, putting iron from iron oxyhydroxide into nickel oxyhydroxide increases the activity because of the bond strength. But I think it's reasonable, but I'm not sure yet.
Yeah, I mean that was suggested by some of the work of John Marcus a number of years ago when he was looking at perovskites.
Yes.
Remember?
Yes. So the challenge, there's been a lot of people who have done correlative studies. The challenge is most of the perovskites actually aren't stable under base. they form surface layers of hydroxides, oxyhydroxides. There's a beautiful study in Science from MIT, from Yang Xiaohorn, working with John Goodenough on perovskites. And they have this beautiful thing, and this this volcano curve, and the thing on the top is optimized based on the surface EG orbital filling of the surface cation. And it turns out that a year later, the whole thing falls. I mean, not a year later, they published a paper showing the whole thing's not stable, and you're forming cobalt, iron, oxyhydroxide at the surface. So I think the challenge is, yeah, all these things could be happening. But when I read all these papers in sum, I'm not convinced that I understand the trends that people measure, because I'm not even sure the crystalline structures they think are there. So I've sort of I've flipped the approach and say, let's target the oxyhydroxide phases, which we think are forming anyways, not worry about the crystalline structure, and let's try to answer sort of the local structure questions, starting from the simplest ones and then work more complicated. But it's a great points.